An m times n matrix is a collection of numbers arranged in m number of rows and n number of columns. Here is an example of a 2 times 3 matrix. It has 2 rows and 3 columns. The exact position of each number is important when attempting to add or multiply. A 5 times 3 matrix looks like this. Matrix B has 5 rows and 3 columns. If we were to select a reference from matrix B, let's say the number 6, we could write B32, B referring to the matrix, 3 being the third row, and 2 referring to the second column. So B32 equals 6. Let's try B43. Row 4 and column 3 gives us B43 equaling 8. And if we were to write all the matrix references as a collective, the matrix would look as shown. Matrices can be added, subtracted, squared, or multiplied, just like any regular equation. The trick is always to know which cells interact. Let's take matrices A and B. These are two 2 by 2 matrices, and then add them. Adding and subtracting are fairly straightforward, in that corresponding cells interact. In this instance, AB11 equals little a plus w. AB12 is little b plus x, and the remaining references follow the same theme. If we were to try to find b plus a, as opposed to a plus b, the order changes slightly. This again is less important in adding matrices, but more important in other equations such as multiplication. Let's put in some figures to show this. So a plus b gives us a 2 by 2 equation as shown, whereas b plus a gives us the same result. Subtracting gives slightly different results. Let's take the same two matrices. A minus b can be written as shown. In subtracting, the individual references in the new matrix match up similarly to when adding. And in reversing, the references switch as seen before. The only difference is the outcome. Conveniently, A minus B leads to a matrix consisting of all negative 4s, whereas switching leads to all positive 4s. In the next matrix video, I'm going to show matrix multiplication, where we will see just why it is so important to keep track of the individual cells.